Okay, welcome back everybody to another video in my series on thermodynamic theory. Today we're going to be talking about the laws of thermodynamics. So we're going to be looking to build up these laws from some of the observations that we've made. Namely, in the first video I did in the series, we derived this function, this probability function. It's the probability of the system, the probability state distribution of the system as a function of energy. We're going to be using this as a starting point to look at and analyze some of the laws of thermodynamics, and we're going to also see entropy in this video. So first we're going to look at the conservation of energy. We're going to look at that one first. We need to show that an increment of system energy epsilon is equal to an increment of internal heat energy, that's what this guy is, plus an internal increment of the amount of work done to the system, which I have alluded to a little bit before. So we're going to show that guy. I might break this up into multiple videos based on how long it goes. We're going to talk about, number two, we're going to talk about the meaning of entropy and its existence. It's a I'm putting an asterisk here, a very simplified view of this law, and we're not going to go into detail on it. And then we're going to ask the question, what happens at t equals 0? Once again, a simplified view that's not extensive at all. Okay, so let's start with the first law, the law of conservation of energy. So what we're going to do is we're going to start with this quantity, this probability function that we've derived. And in this video, actually, we're going to find out what this thing is all about. We're going to get more of an intuition for what it's for. So first, let's take the natural logarithm of both sides. And of course, rules of logarithms and exponents. Take the logarithm, the exponent comes down. Get f minus epsilon over kt. Bring the kt up. And I'm going to write this as k ln p times t equals f minus e. And then I want to rewrite this in terms of e is equal to f plus, I'm going to write this specifically this way, minus k ln p times t. So Gibbs defined, I think this is called the Gibbs entropy. It would make sense since we used Gibbs' method, but Gibbs defined entropy as this quantity negative k ln p. So when we get into number 2, we will talk about it. But for now, we're going to rewrite our energy equation with this definition of entropy. So we see epsilon equals F plus ST. So we have this question that we want to answer about differentials. So what the question is in our equation, what's considered a variable and what's considered something that's constant? Well, we're going to assume for now that T is a constant. The temperature of the system we're going to assume is a constant. It doesn't always have to be in thermodynamic systems, but in this case we're going to choose it as a constant. So a differential in the energy is going to be dF plus T ds. Okay, so we already can see that this is very similar to the format of our conservation law up here. There's only a couple things we really need to note. First of all, and we've discussed this before, we're going to get dW is equal to negative P dV. So I discussed this in a previous video, but it's one way you can think about it is if you're compressing a gas or if you're making dV, the change in dV is negative, then a negative times a negative is a positive, meaning that you will need a positive amount of dW to do that. So compressing a gas needs energy to do so, which makes sense. This is a cogent statement. So this is number one. Number two is basically it's not something we can derive, it's a definition. And to make this Gibbs entropy and this derivation so far consistent with the laws of conservation of energy, we get that P, and this I'm kind of running out of symbols because capital P always also meant probability, but I'm just going to say P average to mean the average pressure. The average pressure is going to be defined to be the partial derivative of the free energy with respect to volume. Okay, so this is, like I said, this is a bit of a given, and maybe I should write this P as well because this is also average pressure. dV. Okay, so to get into to get this guy in the form we want, basically there's just a little bit of manipulation we need to do. Also, entropy, TDS, as a sort of separate definition. We will say that D, an increment in heat energy, is attributed to TDS. Okay, and we're going to talk about this guy real soon and what entropy means. We know what temperature is, but we're going to call this an increment of internal heat, whatever that means, but we will talk about it. So continuing on here, we can see that if, for example, this free energy F is only a function of volume, then we can easily see that dF is equal to negative P average dV. And then we've already seen that TDS is going to equal dQ. And of course, well, we know that negative P average dV is dW. So this is how you can sort of explain, I don't want to say derive, this is how you can explain the first law of thermodynamics from this theoretical viewpoint. But obviously, it's very important that we need to figure out what this quantity S and this quantity P, what they are. So that's going to be important in making sure we understand where these definitions come about. So I think I'm going to cut this video off there and just do a quick short one. But this is a nice quick way to show how the probability density function that we derived can lead to sort of a coherent understanding of the law of conservation, and that it's something that we should observe to be true. And then the theoretical framework that we built, it must be true as well. So so that's it. That's all there is for this video. Please like and subscribe and comment below to tell me what you think.